This example, we have a gas phase irreversible reaction. A plus 2B goes to C. And it takes place in an isothermal packed bed reactor. We're given the composition of the feed, the pressure, and the temperature. And the inlet volumetric flow rate is 10 liters per minute. And it says the outlet volumetric flow rate is also 10 liters per minute. And the conversion is 70% for reactant A. And the question is, what is the outlet pressure? And so essentially in this problem, what we're looking at is there's a decrease in the number of moles in the gas phase, which should result then in a decrease in the volumetric flow rate. And then there's a decrease in the pressure through the packed bed, which results in an increase in the volumetric flow rate. And these two effects essentially cancel each other so that the volumetric flow rate doesn't change. And so the problem really is looking at using the ideal gas law for a flowing system where this is the volumetric flow rate and this is a total molar flow rate. And so as the pressure decreases, the volumetric flow rate increases according to this equation. As the molar flow rate decreases, the volumetric flow rate decreases. So first let's draw a diagram to represent the system. So we're going to apply the ideal gas law, the initial conditions, inlet reactor, and then at the exit of the reactor, what I want to do is divide these two equations. The volumetric flow rates are the same, so they cancel RT constant because temperature is constant. And so this equation says the final pressure is equal to the initial pressure times the final total molar flow rate over the initial total molar flow rate. So we need to determine the values of these flow rates. And what we're going to do is pick a basis of 1 mole. The flow rate is certainly different from this, moles per time, and we're going to look at the inlet. Look at the inlet for 1 mole is 0.25 moles of A, 0.75 moles of B, no moles of C. So the total is 1 mole. That's our basis. The outlet, well, it says let's write it first in terms of conversion. 1 minus X. And for every mole of A, 2 moles of B react. So we have 0.25X. The moles of A that react, and twice that is B. And then C is 0.25 times X. And now, since X is 0.7, I can calculate each of these values. This is 0.075, 0.40, and then C is 0.175. I add these together, 0.65. So now I can go back to the problem. Inlet pressure is 2 bar, outlet molar flow rate 0.65, inlet is 1. Of course, it's proportional to those values. We don't need to calculate the actual value. And so 1.3 bar then is the pressure at the reactor outlet to keep the volumetric flow rate constant.